In the previous video, we discussed a number of different elastic constants, and we talked about how those elastic constants were connected by a range of different equations. In this video tutorial, we're going to look at some practical examples whereby we're going to calculate unknown elastic constants for different materials. So in this first example, we have an elastic modulus of 195 gigapascals, and we have a modulus of rigidity of 75 gigapascals. Our aim here is to calculate the Poisson's ratio for this material and the bulk modulus. In the previous video, we also mentioned some of the equations that are used to connect these different elastic constants, and one of those was as follows: E equals 2g multiplied by 1 plus the Poisson's ratio. Now, looking at the example we have here, we know the elastic modulus and we know the modulus of rigidity, and the first thing that we're trying to find is the unknown Poisson's ratio. So the first thing that we can do to each side of this equation is divide by 2g, and we're going to get E divided by 2g equals 1 plus the Poisson's ratio. Therefore, the Poisson's ratio is just E over 2g minus 1. Now, plugging in the values that we have here, we can work in gigapascals because we're given an elastic modulus in gigapascals, and we're given a modulus of rigidity also in gigapascals. One of the advantages of working with SI prefixes in this way is that we can work with both of those in gigapascals providing we're consistent. The ratio there would remain the same whether we worked in pascals or gigapascals. From that, we're going to subtract 1. And plugging those values into the calculator, we get a Poisson's ratio equal to exactly 0.3. Now, the other unknown that we have there is our bulk modulus, and we have an equation for calculating bulk modulus, which states that bulk modulus K equals E over 3 times 1 minus 2 times the Poisson's ratio. And once again, we can plug in our values. We have 195 working in gigapascals divided by 3. 1 minus 2 times 0.3 is 0.6. And running that through the calculator gives us a bulk modulus equal to 162.5. Now, we know the units here are gigapascals because we inputted our elastic modulus in gigapascals. So there we have an example of how to calculate Poisson's ratio and bulk modulus when the elastic modulus and the modulus of rigidity are both known. Let's take a look at another example. Okay, so in this example, we know the elastic modulus of our material and we know the Poisson's ratio, and this time we need to calculate our modulus of rigidity G and our bulk modulus K. Note that the values given here of 105 gigapascals for elastic modulus and 0.32 for Poisson's ratio is probably more commonly associated with a material such as brass. So first of all, let's calculate our modulus of rigidity, and the formula that we use for this is G equals E over 2 1 plus Poisson's ratio. Now, plugging in our values then, we have an elastic modulus of 105. Note that that's in gigapascals, so that's going to give us a modulus of rigidity in gigapascals, divided by 2 over 1 plus 0.32, giving us a modulus of rigidity equal to 39.77. And once again, that's gigapascals. Next, we can calculate our bulk modulus. And the formula for bulk modulus states that K equals E over 3, 1 minus 2 times the Poisson's ratio. And again, we can just plug in our values. We have 105 gigapascals divided by 3, 1 minus 2 times 0.32, giving us a bulk modulus this time equal to 97.22 gigapascals. So this time we knew the elastic modulus and the Poisson's ratio, and from there we were able to calculate the modulus of rigidity and the bulk modulus. Let's take a look at one more example. Okay, so this time we have an elastic modulus of 175 gigapascals and we have a bulk modulus of 225 gigapascals. We're going to calculate our Poisson's ratio and our modulus of rigidity. In this instance, I'm actually going to calculate my Poisson's ratio first, and we have an equation that links our Poisson's ratio and our elastic modulus and our bulk modulus as follows. E equals 3k, 1 minus 2 times the Poisson's ratio. Note that we're trying to find the Poisson's ratio in this case, so the first thing that we need to do is divide each side by 3k. We get E over 3k equals 1 minus 2 times our Poisson's ratio. So the next step then would be to subtract 1 from each side, and in doing so we'll get the following. E over 3k as a fraction minus 1 equals minus 2 times the Poisson's ratio. Now there's a number of different ways of setting this next step out, but what I'm going to do is I'm just going to put this term on the left hand side in a square bracket, because then all I need to do now to get my Poisson's ratio on its own is divide each side by minus 2. So we're going to end up with a staged fraction where we have E over 3k minus 1 on the top of this fraction and minus 2 on the bottom of the fraction. We can plug in some values. We have 175 as our elastic modulus. We have 3 times 225. Now note, I'm still working in gigapascals, but so long as the top and the bottom of that fraction are both in gigapascals, there's no problem with doing so. From that we'll subtract 1, and then we'll divide all of that answer by minus 2. Now running that through the calculator gives me a Poisson's ratio equal to 0.37. The final step in this example then is to calculate our modulus of rigidity. And as we said previously, our formula for calculating modulus of rigidity states that G equals E over 2, 1 plus our Poisson's ratio. Now, although I've written our Poisson's ratio there to 2 decimal places, I'm going to use my full calculator answer to ensure that I keep a higher degree of accuracy in my answers here. So in actual fact, we have equals 175 in gigapascals, meaning our answer is going to be in gigapascals, over 2, 1 plus, and my calculator answer is 0.370370. I'm still going to write this as 0.37, but I'm going to use the answer function in my calculator, giving me a value of G equal to 63.85. That's correct to 2 decimal places, and that's also going to be in gigapascals because our previous value for elastic modulus was in gigapascals. So in this video, we've seen how we can calculate all 4 elastic constants, providing 2 or more of the elastic constants are known. We've also seen how these are somewhat interchangeable and how we can calculate any of the unknown elastic constants, providing we have sufficient information about the other elastic constants. The other thing that we've seen here is that there's a relationship between the ways in which materials respond when they're subjected to complex loading conditions. We have the elastic modulus, which relates specifically to tensile and compressive forces. We have the modulus of rigidity, which relates to shear. And we have our bulk modulus, which relates to uniform pressure being applied to an object. But what we see is that the way the material responds in relation to each of these forces is actually connected. Now, in the next video, we're going to explore the Poisson's ratio a little bit more and see how materials respond to axial loads in the opposing directions. So, for example, if we apply a tensile force in the x direction, then how does the material respond in the y and z directions? But that's all for this video. Thanks for listening.